Okay. Hi, everyone. Thanks for joining us. I'll start with a quick introduction. Today, we'll be hearing from Professor Bolei Zhou, who is currently an assistant professor at the Chinese University of Hong Kong. Prior to that, Bolei was a PhD student with Professor Antonio Torralba. His dissertation work was titled Interpretable Representation Learning for Visual Intelligence. Many of you are probably familiar with his work on class activation maps, or CAM for short, or some of his more recent work on network dissection, both of which provided us with a better understanding of what was happening inside of our CNNs. Bolei's won numerous awards and fellowships, including MIT Tech Review's Top Innovators Under 35 in the Asia Pacific region and the Facebook PhD Fellowship. Today, Bolei will be talking about interpretable latent space and inverse problem in deep generative models. Take it away.
Yeah, great. Yeah, thanks for the introduction, Arjun. Hi, everyone. So very nice to have this opportunity to meet all you guys. You know, during this quarantine situations, it's good to connect and with people and make new friends. So today I would like to talk about the series of work in my group that's working on the interpretation of deep generative model. So I will talk about the interpretable latent space and the inverse problem in GANs. So, you know, over the years, we see great progress in the field of image synthesis. So first in 2014, the GAN came out. Then over the years, we see the image quality and the content of the generated image have been greatly improved over the years. So you can see we have the style GAN, the big GAN, style GAN V2 that can synthesize all kinds of different objects in very high fidelity. So even people cannot differentiate whether it's synthesized image or the real image. And also there is this very recent progress in image synthesis. The first is this neural value rendering that can like learn some implicit neural representations. Then they can do this to generate different views on the fly. Also this month, we see this OpenAI text to image AI bot that can like turn any written sentence into the image. So you can see here we have an armchair in the shape of avocado. So it's quite amazing that this deep neural network can add their creativities in creating a new image. So we have such amazing deep generative model. So we want to understand why it can synthesize such a realistic image. So it's relevant to the topic of today. So here we have a deep generative representation. So, you know, previous the OpenAI bots, they have billions of parameters. So the model itself getting larger and larger. So it can synthesize more and more realistic image. So we try to understand why this realistic image can be synthesized, and also giving this representation, deep representation, what have been learned inside. So here I show a very basic generators. So here we have a GAN generator. So this generator basically is just a convolutional neural network. So we have some inputs latent vector. So those input vector usually sample from some random distribution. So it's a 512 random vectors as inputs, then throw into the generator. Then this generator can synthesize this realistic image. So here we have a generator that generates the bedroom. So there are two kinds of latent representations in this case. The first kinds of latent representation are the latent units. So here I call this convolution filters in the generator as a latent unit. There are another latent space is this latent vectors that is sampled from this random distribution. So they are the latent space. So towards the understanding and visualizing of the latent units, there is this amazing work done by David Bao and Antonio Torralba from my previous lab that's try to visualize the internal filters. So they show that when we train this generator to synthesize the scenes, the internal unit actually emerge as object synthesizers. So some units specialize to synthesize the clouds, some to synthesize the door and the grass. So then we can turn on and turn off the unit activation, and we can control this generation process. So on the right, I show you an interactive interface that we can turn on and turn off the unit with the semantic meanings, then adding or removing the content. But how about the latent space? This latent space, 512 latent space, it's actually the driven force for all the generation process. We first sample the random vectors from this distribution, then throw them as the inputs, then into this generator, then it can synthesize a realistic image. Then the probability is what have been encoded in the very beginning latent space. How can we identify the subspaces inside this latent space? So here I have first have a very initial experiment in this latent space. So here is just a random walk in the latent space. So basically each time we just add some increment on top of the latent vectors. Then you can see the output image actually change according to this random permutations at the beginning. So you can see the synthesized images contain a lot of different semantics, like they have different views, and also the number of bed will change, and the texture of the sheets, and even the background will change according to the permutation in this latent space. So that makes us think this latent space indeed encodes all kinds of semantic concept, semantic information about the rules. If we can go back, identify those meaningful subspace, then we can actually steer or control this generation process. So, given this nature scenes, there are a lot of semantics inside the nature scenes. So my previous work, in my PhD thesis work, so I work on this visual scene understanding. So for this visual scene understanding is a very classical topic in computer vision, and people build different models and extractors to get all the meaningful semantics from this input image. For example, we can have this image level labels. So this is a bedroom, and we also have different attributes, the nature, lightning, wood, tide, and also we can generate this 3D structure, or you can see it's 2.5 dimension structure information like layout to describe the things. We also can apply the semantic segmentations to extract the object and the regions. So you can see for this synthesized image, there are all kinds of different semantics. So if we can link those semantics meanings back into the latent space, that we can control this generation process. Also, another very interesting thing is that when we train this model to do this kind of image synthesize, we don't have any other external supervision. They just learn to synthesize the image by itself. So whether this internal representation already learn all those kind of the different multiple level of scene descriptors is also unknown questions. So along with my students, Yang and Shen, so we propose some framework to identify the causalities in the latent space. So basically giving this image generation pipeline, we can apply the off-the-shelf predictors and to extract many semantic informations from the synthesized image. Then we can go back into the latent space and identify the cause effects relations. If we can identify the dimensions or the subspace in the latent space that can control the relevant to the final outputs, then we can control the generation process. So we propose a framework. It's a very simple framework to interpret the latent space. So basically, we first generate a lot of latent vectors from this latent space by sampling from this random norm distribution. So just a Gaussian distribution. And then we can throw into the generator. Then this generator will generate a lot of images. And we have this image space. And then we apply some off-the-shelf classifiers, from the places Kubernetes previously I built, or some other like something attribute classifier. Then we can predict different attributes for the synthesized image. So here we just adapt some indoor classifier. So we can have the label for whether it's indoor lightning or outdoor lightning conditions. So we treated this predicted label as a pseudo label for the latent vectors. Then we can go back into the latent space, then train some classifiers. So it turns out this linear classifier can achieve a pretty nice classification accuracy for this binary classification, whether it's indoor or outdoor. Then we can achieve more than 90% accuracy by using those pseudo labels. So it also shows that this latent space have a lot of disentangled semantics. They already disentangle different semantics. Therefore, we can achieve such high accuracy. So we have another very important step. So here I call it counterfactual verification. It means we have to change the latent code and observe the output, whether this boundary really control the steps. So we have this verification step, so very important step. After we add some increments through this boundary and to see whether this image attributes have been changed, then we can use this to measure how well it controls some semantics. So through this process, we can identify the reliable boundaries in the latent space control different semantic meanings. So here we first have a boundary that controls nature lightning and the indoor lightning. So here I would like to show you some visualization. So let's see if we have two random vectors in the latent space. So at the beginning, they have they are look like this. In each one of the image, you can see there is a lamp inside. So here we gradually push the latent codes toward the boundaries. So by adding just the norm of these boundaries, so you can see the lightning condition gradually change. So the lamp inside the scene just turned on. So here is a more like a demo video of this. So you can see a very beautiful this continuous change of this lightning conditions. So not only the lamp is turned on, also the global lightning condition is also changed. So you can clearly the shadows projected on the wall. So it's much better than the simple Photoshop results. So in this latent space, not only we identify the indoor lightnings, we can also identify many other attributes. For example, we can identify the boundaries for clouds and the long clouds, and the boundaries for vegetation and the long vegetation. Then after we identify all the different boundaries, then we can change their semantics. So here I show you another demo video of aiding clouds. So here we have some images, so it's have very blank backgrounds. So the weather condition seems not that well. So right now we want add some cloud inside. So here is a video that we just push the latent code toward the cloud boundaries. So you can see those clouds are more like automatically grow out in the sky, particularly for the second image. So I really like it because you can clearly see this very beautiful sunset color projected on the clouds as well as on the buildings. So it's a very realistic manipulation. So here is some other results that we have some buildings that it's very boring because it lacked vegetation. Then we want to add some vegetation inside. Then we can push the latent code towards this vegetation boundaries. Then the grass and the trees are just more like automatically grow out in a sense. Also very interesting, you can see for the first example, so you can see this generator is smart enough to put a sidewalk on the grass because there is a sidewalk for people to walk. So you can see from this image synthesized supervision, the generator itself actually learn all this kind of composition of concepts. So if we can go back into the latent representation, identify them, then we can control the different compilation of the visual concept. Another very important innovation in the deep generative model, I will see is layer-wise stochasticity. So, before that, so we have this DC GAN and the PG GAN. So the latent vector is actually at the beginning. So the stochasticity is at the beginning, and then we throw this latent vector into the generator, then we can synthesize the image. Then there is a recent model, StyleGAN and the StyleGAN V2. They utilize this layer-wise stochasticity. I think this is one of the biggest innovation for generative modelings. That's previously we have this driven force at the beginning, but for StyleGAN models, they have this constant at the beginning. They just add new latent vectors through each layer. So each layer, they will add some latent vectors inside. Then through this kind of things, layer-wise stochasticity, they actually encourage this disentanglement across the layers. So right now we try to further understand how each layers capture the visual information. Then we apply our framework to the layer-wise latent vectors. It actually we discovered that there is a very clear semantic hierarchies emerges from this thing synthesized. So after we apply our method to each latent vectors at each layers, we actually observe each layers correspond to different level of semantics. So the plot on the left show you that the importance of at each layer. The horizontal axis is the layer depth. The deeper is closer to the image. The vertical axis show you the importance to some level of semantics. So right now we have this layout level, object level, attribute level, or color scheme level. So you can see in this deep generative representation, the early layer actually controlling this layout. So this is the layout of the things. Then the middle layer controls the objects and the attributes, and later layer controls the color scheme. So it's roughly correspond to how a human paints the image. You know, when human we decide to draw some image, we will first determine the layout of the scenes. Then we will start outline this object inside. Then we will start colorize and determine different textures of the object. So this deep representation is also doing the similar things. It first decides the layout, then determine objects, then add those texture and the colors. So here I show you some demos that we apply our method to different layers. And so here, after we identify the factors that control the layers in the early layers, then we can control their layout. So here I show you this layout control result. This result is interesting because this deep generative models, we just train this model on those unpaired data. So training data are just those individual bedroom that's downloaded from the web. So we don't have the multiple views for the same environment. So it's just unpaired data. So this generative model just kind of learn those 2.5 representation structure information in order to synthesize the image. So if we can go back to identify this steerable dimensions, then we can control this layout. The result is not perfect. You still can see there are some artifacts, like some lamp on the right, just missed out. It's just that we don't have any explicit supervision on this. But this result already impressive enough because we don't have any external supervision on this multiple views information. Now we can control this structure layout. So here is another one. In the middle layers, we can control their object. So, you know, well, for people like this living room and bedroom, so usually it's object inside differentiates the two categories. Like we can totally move out all the furnitures like the bed, and we can change this room into a dining room, right? We can just move out the bed and move in the table and the chairs. Then this environment will become more like a dining room. So this deep representation also doing the similar things. The intermediate layer, they will determine which object to put inside. Then we can push them across category boundaries, and the object inside will also change. So here I would like to switch gear and then take a look at another model. So here we have this model for scene synthesize, for face synthesize. So we train on the faces. then we have this face synthesized model. So we also have this recent work that we want to control and identify the steerable dimensions in the face scans. So we have this work called interface scan that bridge the latent space between the generators and the attribute space. So the framework itself is also very similar, but we analyze different semantic the relations between different facial attributes. We actually identify there are some attributes they are more entangled with each other, and this is more for some attributes it's more challenging to manipulate. So after we identify those different subspace that control the face, then we can doing all kinds of visual editing. So for example, we can make the sky cooler by add some ice glasses, and also make the lady look younger, and also make this person like front face. This result also interesting because when we train this face scan, we don't have this pairwise data. So this model just identifies this different views of the persons, and we can just push this latent code and then change the views. So here we can also make this more man. So here I show a quick demo of this video. So here is this demo video, like we manipulate the face. Here we just push the latent code, and we can change the views of the face. So it's very realistic. Here, any questions so far for this part? So while I play this demo, so if there are any questions, so I can respond.
Yeah, there's a handful of questions.
Yeah.
Back when you were introducing the topic, someone asked how it's related to disentanglement.
Yeah, that's a very good question. So the disentanglement, it's just more like a emergent behavior inside the latent space. So right now we just take this pre-trained model. So we don't introduce any disentanglement mechanism. So we just discover that the latent space, they already disentangle itself for some of the attributes to some degree. So right now we are working on some new disentanglement mechanism to encourage this process that we can further improve this manipulation result.
Cool. There's another question about mode collapse in GANs, and maybe what you think about that, I guess, in general.
Yeah, the mode collapse is a very common phenomenon for GAN. So, the GAN is this adversarial trainings. So sometimes it will throw some modes of the distributions. That is even that also happen in the VAE, variational autoencoder. So in our case, we just take the pre-trained GAN. So the pre-trained GAN, it may drop some modes, but still for majority of the image, if we can synthesize this high quality image, then we can interpret their latent space. But indeed, in the latent space, we found out there are some like pitfalls inside the latent space that they will, if we sample from the subspace, then the output image will be quite bad. So there will be some future work that further explore this long convex properties of the latent space.
Oh, neat. Okay, we can. There's two more questions about that part, and then maybe we can move on.
Okay.
One is can you describe how changes to the latent code are done during inference? So during inference, the latent code is a random Gaussian. How is fine-grained changes added to the latent vector to control object level changes?
Yeah, so here we just have this linear summations. So after we identify the boundaries, we just train some linear SVM. So it's just another vector. So we just add those vector on top of that. So it's a very simple process. So you can check this our source code to see this process. It's very simple.
Okay, and then one last question. It seems that the foreground does not change when you change the latent vector according to the boundary. How is this achieved?
The foreground, So that relevant to at which level we change. For those attributes that describe some local regions, so we can change the latent code at later layers. The early layer will control more like global effect of the image, but the later layer, they control more fine-grained attributes. Then we can control at those later layers.
Cool.
Okay, great. So let's continue. Then we move into this inverse problem of GAN. So, previous work, they just work on this synthesized image. But in practice, we want to work on the real face, right? So we want to work on my own face. So here is my my profile photo many years ago. I have more hairs now. So here is my previous profile photo. So right now we have this GAN inversion problem. So it's an inverse problem for generative model. So it's giving this latent code. We want, or giving this image, we want to invert back into the latent space, right? Previous generation is we sample from the latent code, then we can have this synthesized image. Right now we have this real image. We want to go back into the latent space, identify the latent code. Then we have this inversion problem. Then if we just take this naively, then we can simply solve this minimization problem. This latent code, we can simply optimize this latent code, then we can reduce the distance between the given image X and this synthesized image. So it seems quite easy, right? We just optimize this. Then I first try this GAN inversion. And so here is my real face I throw inside. And so right now I get this optimized code after many iteration of the optimization. So let's take a look at how this idle optimization work. So it actually synthesizes some image like this. So that is a reconstructed face. So let's put this face side by side with my own face. So you can kind of see this minimization problem is already hard, so try to synthesize my face, but clearly it's not me. It's more like a Western version of me. So you can see the color texture seems the same, but the identity of the person just more like a Western brother of me. And so, when something doesn't work in machine learning or deep learning, we should try it again. So here I try different random initialization. This Z actually have big effect on this optimization problem. So here I try different random initialization. It just synthesize all different version of me. So also it clearly shows there are some bias in the data set or in the model, in the generative model, because this generative model, they just train on this Cerebral HQ data set. Those data sets only contain the Hollywood actors. So, in this Hollywood, there are not so many Asian actors or actresses, so they cannot understand this attribute for Asian people. So we want to address this issue. So it's this GAN inversion is actually quite a challenging problem. So we want to fix this. So about 1 year ago, there is this method called image to style GAN. As I previously said, there is this style GAN. They will use multiple latent codes to reconstruct the input image. Then this method, they actually optimize the latent codes at different layers. Then the dimensionality of the latent space is greatly increased. Through this kind of optimization, the synthesized, the reconstruction quality is greatly improved. So you can see here, this image to style GAN, it kind of work. So when we use a larger latent space, like 14 by 512 dimensions of my face, can reconstruct it. However, there are some overfitting issues or observed for this. Here, this generator is purely trained on human face. So here I test on some long face image. So here I throw some cat image inside or some bedroom image inside to do this inversion. It turns out this image to style GAN can still reconstruct the image. This seems quite amazing, like too good to be true, right? So you can synthesize all kind of long face image when this generator doesn't even see this in the training stage. So, but they're still saying that this process seems just overfit this target image. So here we have some identified the overfitting issue. We found out that the inverted latent code from this image to style GAN, they cannot well support the latency manipulation we just introduced in the first session. That's after we invert the latent code, then we add some boundaries on top of the latent codes, then we cannot achieve this realistic manipulation. So here is some examples. So we have this image, a reconstructed face, then we add some smell vectors or glasses vectors. So the quality is really bad, which means the inverted code doesn't very well support this manipulation. So the issue is this optimization problem generates some out-of-domain latent codes. So here, this optimization itself is a unconstrained optimization problem. So we optimize this. So we may end up some latent codes indicated as the red points. It's made outside of the original latent space. It's outside of the domains. Then it's outside the latent space. Then we cannot apply the previous manipulation boundaries to this out of domain latent codes. So right now we want to fix this. For this GAN inversion, the fundamental issue is actually the GAN itself lacks this inference ability. In VAE, they have this encoder, but for GAN, there is no encoder. So over the years, people try to add the encoder to the GAN generator. Take this pre-trained generator, they just train some encoder. So there are a lot of previous work that doing the similar things like big by GAN. They add some encoder to the big GAN models, then they can do this feature learnings. Also, this last year's adversary latent autoencoders also doing similar things. Also, recently we have this work train some encoder. So you can see this reconstruct result from the encoder. It seems not good, and the quality seems improved over the years, but the result is still not good enough. You can clearly see the identity of the reconstructed face is still not the same person for the inputs. So here we have this recent work, the GCCV work last year, that we try to combine this encoder method with this optimization methods. So we propose this encoder constraint optimization. So previously we have this unconstrained inversions. Right now we add extra terse insights. So here we simply treat this encoder as a regularizer for our reconstruction step. So you see, besides the first reconstruction, we also have the second terse that we want to constrain the latent codes back into the latent space. For this synthesized images, we want to put into the encoders. The encoder will regress this latent code back into the latent space. So we add the second terse as a regularizer for this latent inverted latent code to enforce the latent codes back into the original latent space. So this kind of regularizer works quite well. So here is a comparison with the image to style GAN model. So you can see the reconstruction results is improved. Also, more importantly, the manipulation results is also greatly improved. You can see here we can manipulate different attributes for the same person. And so here is a demo video for the manipulation results. So here we can change different expressions and also change the pose of the real person. So right now all the person are real person compared to the previous one is just a synthesized result face. And so here we also have some interpolation results. So giving two faces, we can do this very realistic interpolation. After we invert both the latent codes, then we can just weighted sum for the latent codes to combine the two faces. It's more interesting that we can also doing this scene interpolation. So here we compare our results with latent codes from inverted code from image to style GAN. So we can achieve much better results. we can like generate some intermediate like building style between the two. Also, the result is much better than the image to style gun. Also, we include some new application based on our method. It's called semantic diffusion. So it's more like right now we want to take the foreground face and the background face. So we just copy and paste and stack on that. If we directly copy and paste, the result is really bad. So what we are doing that we can include this optimization. We can put some mask. So here, this M indicates the mask. So right now we want keep this mask, the foreground mask, as the same as possible. Then just let the background adaptive to the foreground. So then you can consider this as a diffusion process that we want to preserve the foreground and let the foreground information diffused across the background. So after this kind of in-domain optimization, then we can make this background automatically adapted to the foreground. Then we can create this very coherent image. So here is some demos, the background, directly copy and paste, and doing this optimization, then we can get a very coherent foreground. The background, the size and shape will also adapt it to the foreground. So you can see here, we have this unicorn and Mona Lisa and my own face. So I really like this long hair style. You can use this to change your own style. That's why I'm just grow my hairs, want to have a long hair. Also here we propose some demo. So because due to the time limit, I cannot run this demo. So we have this Collab. So you can go to this Collab and upload your own image. Then you can try different kind of hairstyle or different background styles. Based on this semantic diffusion, we also can use this to do the scene harmonization. We want to like change a new bat in this scenes. Then we can just copy and paste some bat inside and doing this mask in domain optimization, and this foreground this background will be adapted to the foreground. And here we want to change copy and paste a new window, then it will directly copy, adapt this background to the foreground and form this very coherent image. Okay, so I think we're getting to close to the end of talk. So here I would like to promote another recent library we released to facilitate the research for generative modeling. So here I call it GenForce. So it's a generative modeling for everyone. So my students have implemented PyTorch libraries for this generative modeling. So it provides many different models. So I have a model of more than 60 pre-trained models with Collab live demos. So also provides the training codes in PyTorch for StyleGAN and StyleGAN v2. So you can see here I generate some very cool visualization for the interpolation. So I really like this kind of interpolation. So here each small window is from a different model. So I can watch this kind of interpolation for whole day. But still they tell us that this different model, they have different semantics. So our previous work, we just use this off-the-shelf predictors to identify the latent space. But for those different like animation and animals, we don't have this trained classifiers. Now, how can we further identify the steerable dimensions in those long face, long bedroom images for all kinds of models? So here, we want to identify all the steerable dimensions for different models. So we have this very recent work that it's a method that's doing this unsupervised discovery of steerable dimensions. So we look into the representations of the generators and try to factorize the meaningful dimensions from these representations. So based on this work, we build some interactive interface that user can interact with this generative model to do this collaboration, like interactive content creation. So on the left is this different identified steerable dimensions, and we can change the pose of this animate characters and even the size and the shape of this animation. So it's very cool results. So we also release a code so you can check it out by yourself. Also play with this demo. So here is some acknowledgement. So working with my very amazing students, Yujun, Ceyuan, Jiapeng, and Yinghao. We also release this all our codes and papers at this GenForce page. It's a research initiative on generative modeling because I really believe in the power of generative modeling. So here I have this slogan here. So may generative force be with you, because I believe this generative modeling can really improve this field of computer vision. Okay, so may generative force be with you. So that's end of my talk. So I'm happy to answer any questions you may have.
Well, that was great. There was a handful of questions for this part. When you were introducing the topic, someone asked, why can't you use your trained encoder to find the vector of your face in the latent space, which is similar to what you did using an encoder as a regularizer. Could you just train the encoder itself without the other term in the loss?
Mm-hmm. Yeah, if we just use an encoder to reconstruct that, so quality, so I go back. So the quality is actually here. The encoder itself cannot reconstruct the result very well. So here I show some encoder outputs and reconstruct them from the direct outputs of the encoder. This AOA. So this is a reconstruction. Also here is our training encoder. Although we have some improvements over the encoder, this result is still not that good. This also makes a lot of sense, because if this encoder can reconstruct the image perfectly, it's more like we have a perfect image compression method. Like give me any image we can compress into a very short latent vectors, then we can just beat this JPEG or PNG compressions, right?
Yeah. When you were showing some of the dataset bias results, someone asked, could the reconstruction here in the inversion case be thought of visualizations of different dataset priors and biases?
Mm-hmm. Yeah, that's a very interesting question. So it's indeed there is this dataset bias. So through our in-domain inversions, it can sort of overcome this bias. It's more like they can borrow some other features to fill in the gap to reconstruct the content. So that is my takeaway on this, but still this bias issue in the generative model is worth exploring. We have some recent work that we analyze this fairness of the deep generative representation. So we found out even there are a lot of this algorithmic bias in the generators. So there should be further work and explore these directions.
There's a question, do you find that the latent codes of cat/bedroom are significantly outside of the priors for a network trained on faces?
Yeah, we analyze this. So we do this like test-knee visualization, like for this face generator, we throw a lot of bedroom image inside and doing this reconstruction. And then we combine this with original latent codes, then do this test-knee visualization. So we found out they clearly form like two clusters. So which shows that the inverted latent codes is indeed outside of the original latent domain. So that's why after we introduce the encoders, we can sort of like push them all more closer to each other.
Yeah. Makes sense. So the next question is there a class of priors, for example, Gaussian, being imposed on the encoder? Wouldn't one want to ensure that the encoder itself covers most of the true latent distribution and doesn't suffer from some kind of mode collapse or similar issue?
Yeah, that's a great question. So the Gaussian priors is indeed a very important prior. So actually in the image to Stalgan, they use this Gaussian prior. Like they have an initialization, this initialized codes. They just have this Gaussian mean. But the issue is this latent, after we have this layer-wise representation, they introduce some style gun. They introduce some several layers of fully kinetic layer to further generate intermediate latent space. So after we sample from the Gaussian distribution, they will throw the latent codes into like 3 or 4 layers of fully connected layer. Then they have the intermediate latent space they call the W. So this W latent space distribution is unknown. So in that case, we cannot use analytical form to form this prior distribution. And we just use the encoder to approximate this intermediate latent code. So that can help us, the output of the Trinity encoder will output some latent codes that's closer to this intermediate latent space.
Makes sense. So the next question is, what's your outlook for these methods to be applied to other kinds of art form, animations, text, music, etc.?
Yeah, that's a great question. So that's actually follow my recent work to this. So, we have so many different images, different art and oil paintings, and also the generative model have been adopted in many different domains like music generation, text generation. So if we can better go there and identify their disentangled or variation factors, then we can better steer or control this process. So that will let people work with this AI model to do this collaboration, like a human AI collaboration. This is actually one of the future direction I'm pretty excited about, like how human can work alone with the AI model to create new content, not only limited to image, also limited to other, this graphical design, the logo design. Recently, this OpenAI, this text to image model, they provide some directions. They have this text into image, then they can do this generation. But still, this kind of text to image is still not steerable enough. So if we can better interpret the latent space, then we can better customize the output we want. Then we can realize this human AI collaboration.
Yeah, that would be very neat. Okay, where do you think VAEs fall short compared to GANs?
Yeah, that's also a very great question. So the VAE, so in terms of image quality, the VAE is not as good as GAN. But recently people start use some tricks or some method to improve the VAE. Like they have this VQ VAE that they quantile the latent space. This is actually very interesting directions. They quantile the latent space. Previously, the latent space is just a continuous space. They enforce some quantization inside this latent space uses vector quantization. So it's some idea from long time ago in image processing. They want to better generate the codings for the latent space. So then they can use the quantization to formulate that. Then they put some transformer inside this latent space to better structuralize this latent space. Then they can improve the image quality. So that actually gave us some hint that if we want further improve the GAN models, we can also formulate some structures latent space. Then we can have better image quality. But it's interesting to see the future convergence of both VAE and GANs have a more like a unified models.
Yeah. With respects to the first half of the talk, how many attribute classifiers do you train? Are there many one versus rest classifiers, or is it one big multi-class classifier? I would imagine it's the former. Thanks.
Yeah, great. So that's a good question. So for our scene synthesize, we apply the scene classifiers and the scene attribute classifier. So the scene classifier, scene attribute classifier is actually derived from Professor James Hayes' some scene attributes. So there are 102 attributes. So we just train attribute classifiers for each one of the attributes. So we have 102 attribute classifiers, and then we apply all of them to some models. but we have this verification step. So we found out about 10 attributes will align with some models. Because some like indoor things, they don't have this openness or other this like sunshine attributes. So they only there are about like top 10 attributes will have very well control on some models. So for different models, the importance of the attribute will be different. Like for the outdoor things, the outdoor attributes will dominate more for that. But usually we will get about 10 attributes that is steerable and controllable. For the face model, we have about, I think in our paper, we test only about 5 or 6 facial attributes, but we can continue to add more. But here we just treat each attribute as a binary attribute.
And there in the face side, are there also some attributes that are not steerable?
Yeah, we found out some attributes is not that steerable. Also, they are not steerable in terms of they entangle with other attributes. Like we found out like age and gender are coupled, and the age and the glasses is also coupled. Like you increase the age of the person, then there will be glasses like show up. It also makes sense because for those elder people, they will wear the glass, so they will have this coupled attributes.
Yeah. So as we get more disentangled models, we'll be able to steer them even better. That's interesting.
Yeah, exactly.
Okay, so that's all the questions. I might have missed one or two, but that's all the questions I see right now.
Great. Okay.
Yeah, so thank you very much, and I think we can end the talk there.
Yeah, great. Yeah, thank you, everyone. Bye-bye.